How you doing, guys? Welcome to another video. This is topic 5, energetics, thermochemistry, and in this video we look at how do we measure energy change. Let's go. Alright, 5.1, we look at heat as energy, we talk about specific heat capacity, and we look at an exo and endothermic reaction. The IB understandings is about heat and about the temperature and how that impacts the kinetic energy, and also we need to talk about what is an exothermic and endothermic reaction. Now, energy is the measure of the ability to do work, and heat may be released during a chemical reaction. Now, when we have heat in a chemical reaction, that generally increases what we call the kinetic energy, the speed of the molecules. So temperature is a measure of the average kinetic energy of the particles, and that's displayed by a Maxwell-Boltzmann distribution, which is shown below. So we can see with the curve on the right that if we have a whole bunch of particles in the middle, that's the average kinetic energy, the tip of that peak. Sure, we have some that are moving really fast, and we have some that are moving very slowly, but on average, most of the particles sit in that middle section. If, however, we start to change the temperature, so increase the temperature by as little as 10 degrees, what we are doing is we're shifting the curve to the right. So that means that more particles, on average, have a greater kinetic energy. Again, we still have some that are moving very fast, and we have some that are moving very slow, but on average, the majority of the particles have gained an increase in kinetic energy. Remember, the kinetic energy is the energy of movement, how fast these things are moving around. As we heat them up, the particles move a lot faster, so that means their kinetic energy increases. If we have a look at the graphs on the left-hand side, we can see that if we put a dotted line, we could see that at 20 degrees we have a small number of particles in that area of the graph, whereas at 40 degrees we have a lot more particles in that area of the graph. So we have more particles that are moving on average more quickly. Another important aspect for chemists to discuss is the different environments where the heat might be transferred. So we have what the chemists call a system, and that's the area of the interest and the surroundings. Everything else is the universe. Most chemical reactions occur in what we describe as an open system. That's where something wouldn't have a lid, and it can exchange both heat, energy, and matter to the surroundings. Remember that in a chemical reaction that energy is always conserved. There's never a net loss or gain of energy. So if the system is losing energy, then the environment must be gaining the energy. So here we have a diagram which would be an open system because it doesn't have a lid, and there are two possibilities for this open system. It could gain heat, or it could lose heat. So there's heat gained by the system or heat loss by the system. Now, if something gains heat, if the system gains heat, we describe that as being an exothermic reaction because the reaction is releasing energy. If the system loses heat, then we say that that is an endothermic reaction. It's starting to get colder, so the reaction is absorbing the energy. So in the first diagram, if we need to put in energy, that would feel like this is starting to get cold. It's draining out energy from the surroundings. So it's going to absorb energy, which we would feel as cold. So it's getting cold. It absorbs the energy, and we describe that as being an endothermic process. If we have a reaction and it releases energy to the system, it starts to feel hot. It's making the system hotter. So it's releasing energy, which we describe as being exothermic. Specific heat capacity with the symbol C. We can calculate the gain or heat lost by a system using this specific heat capacity. The specific heat capacity is a property of a substance which describes how much energy is needed to raise 1 gram of the substance by 1 degree Celsius or Kelvin. It's the same either way. It's given the units of joules per gram per degree Kelvin or per degree Celsius. Water has a fairly high specific heat capacity of 4.2 joules per gram per degree Celsius or Kelvin. And we can see that there's a number of different samples down there. Now, what does this mean? Okay, well, this little monkey, he is jumping across the sand. Why? Because the sand absorbs a lot of energy from the sun. It has a low specific heat capacity, which means it heats up very quickly. Something like water Water has a high specific heat capacity and it has the ability to absorb a lot more water, so its temperature change would be a lot less. If we know the specific heat capacity of substances, then we can determine the amount of energy in joules required to change the temperature of a given mass of substance. Now, water is in the data book, but if there's something else they want you to use, they'll give it to you in the question. So the formula for specific heat capacity is Q, the energy, equals the mass in grams times the specific heat capacity times the change in temperature, the temperature difference. So here's an example. Calculate the amount of heat energy needed to increase the temperature of 1 kilogram of water from 25 degrees to 60 degrees. So Q, the energy, equals the mass times the specific heat capacity times the change in temperature. Our mass needs to be in grams, so 1 kilogram is 1,000 grams. Our specific heat capacity for water is 4.18, and our temperature change here would be the difference between 60 and 25. I'll put it in the equation so I minimize my chance of making an error. So that gives me 146,300 joules. Now, most of the time we would like to convert that to kilojoules. It's a lot more usable, so that would be 146.3 kilojoules. To go from joules to kilojoules, we want to divide by 1,000. Now, if the same amount of energy had been used to heat 1 kilogram of sand, what would be the temperature rise in the sand? And this will explain a little bit about that image of the monkey on the other page. So what we need to do here is rearrange the equation. We've got the Q equals mc delta T. Our energy is the same from the question above. So Q equals mc delta T. Let's rearrange the formula to make delta T the subject, the change in temperature. So that would be the energy in joules divided by the mass times the specific heat capacity. So the energy, we keep that in joules because we're using the equation, 146,300. We divide that by our mass will be the same as the water, so 1,000. And then the specific heat capacity of sand was given in the table on the left-hand side, which is 0.48. So the temperature change of the sand, if it absorbed the same amount of energy of the water, is 305 degrees. So that sand is going to be extremely hot, which is why the monkey was jumping all over the place to get off the hot sand. Okay, volume 1, some top tips. Energy of Q is in joules, remember that. Take care with the units, and hot means exothermic, cold means endothermic. Thanks for watching, guys. Don't forget, drop a like on the video, subscribe for more, and I'll see you next time.